another electricity video. Okay, I'm probably going to make the other two private because for now anyway, so probably not helpful. It's just too many mistakes, and so starting over. Got to do that now and then. Yeah. Sort of getting back to my old theme because the new one just didn't make any sense. I mean, it's not that it didn't make any sense. It just didn't work. So there's a couple of different things I wanted to get to. So I guess to start with, just draw a simple picture for starters. All right. So let's say this is a wire with electricity going through it. Now, if I was to say, so voltage is basically pressure, and it's the pressure of the electrons. So a positive pressure would mean that you have too many electrons by a certain density, and then a negative pressure would be an absence of electrons by a certain density. So I guess the better drawing to do first is the conductor kind of drawing. So the idea is that conductors are, wires are generally speaking round, but there are going to be some geometric shape. It really doesn't matter what it is. And the point is when it's when it's charged, like there's an excess of electrons at any one point in the conductor. There can be different places, there can be different voltages. What's going to happen is the conductor is going to dictate the shape, is going to dictate the arrangement of where the charge is, where the electrons are in higher density, and where the butts are sticking out, the protons are sticking out, without electrons. So if I was to positively charge this, if this section of wire cross section of wire was positively charged, meaning it had, see, this is the trick, that means it has a lack of pressure, a lack of electron pressure. It's short electrons, very short. So if it's very short electrons, the negative will be here in the core, because you can get by with fewer in the center, and then you can have all these extras would be on the periphery. So this would be the plus charge on the outside of the wire, because the protons can they can balance this way. If the few electrons try to be on the outside, then you wouldn't have enough electrons to go around. So you can have fewer electrons, you can have more sharing if you put all the electrons in the center and have the excess radiate out. So consequently, logically, the same is true for a negative charge, in that the extra electrons wouldn't be any good in the center, but if you put them on the outside, then you can have lots of extras, and it's not going to cause a problem. So now all the protons would be in the center, and a higher density of protons in the center than and a higher density of electrons on the exterior. So in the conductor, when it's charged with a currents going through it, it has a voltage range. So let's say this was 150 volts of positive pressure. What that really represents is that the ground is electron heavy. Okay, so let's call this the ground, the neutral, because we're not going to a negative voltage. And it does matter. It always seemed like the neutral doesn't really matter, but the neutral is a real thing compared to the positive and the negative. And the difference will be seen in this drawing, I think. I'll be able to represent that. So what's happened, like this could be a coil of wire, or you can just think of it as a straight conductor, but it would be a progressive coil, one that coils in a direction. And so if it's positive 150 volts, which means that it is short protons. So the protons are doing this thing. They're on the outside, so it's plus on the outside. And as you get closer to the ground, you get closer to less voltage. So it's 150 volts at its highest potential here, But if you were to tap it at some other location, the voltage would appropriately drop because of the resistance of the conductor. And just logically, you can kind of understand the pressure is going to be, there's going to be a higher pressure and then a lower pressure. Those are the two ends. You have pressure at one end and no pressure at the other end. So obviously it's going to gradate through that to a balance. It's trying to achieve balance, and you'll keep shoving extra in here, and so it's going to keep migrating. As it migrates, it gets finally to a balance at this other end. So this surface plus gets less and less and less and less and less until there's no surface plus. Alright, now if it was a conductor, if you're going from 150 plus volts to 100 minus 150 volts, then you start to see what's really happening, which is the wire is essentially being turned into a magnet. You know, and it has a, these are really the two poles of the magnet. So this is your north and this is your south. I think that's the appropriate designation, but it doesn't really matter. And you'd have the same effect here, except here you're going to have plus voltages on this exterior, and then they'll get weaker, and then they'll cross over, and then it'll be minus voltages on the outside. So here in the center you're going to have that crossover point, and you know, these are pluses, plus, 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 plus. And so this, then you get the real idea of how this is really just a magnet you're creating, and that you end up with a you know, the shortage at one end, the excess at the other end, and the dynamic will be different. So the negative will be going in the core here, and the positive is in the core over here. So you just mark that some way to get the idea of it. So the core of the wire and the exterior playing vital roles in this magnetizing of the conductor. So that's that's basically the conductor being turned into a magnet. So whatever size it gets, it just turns into a dipole. It doesn't, unlike regular magnets where you just break them and it creates a new conductor. This is the same idea, but you won't have the same negative voltage, so you won't be able to create, you'll create a monopole instead of a dipole. Well, it's not even a monopole. It's a dipole, but it's not a full magnet. See, this is like a magnet, except it's like one pole of a magnet, but it's not, because it does get progressively lower. So it has this high potential at one end, high pressure, and no pressure at this other end, where a magnet would have an inverse relationship. There would be, so if these were polarizing filters, it would be, you know, the green or blue on one side and the red on the other side. It wouldn't just go green to nothing, where that's sort of what a regular conductor is doing, that's not going from plus to minus voltage. Alright, so to get to the real point that I was trying to illustrate, and maybe I'll do it with a coil instead of a straight wire. It might get me into trouble, but we'll see. So the idea is you would pile two coils on top of each other, but they're both progressive in the sense they're progressive in the same way. So whatever you do to one, the other one is up is up and down is down. The progression of the spring, so to speak, is in the same direction. It has the same directionality. It isn't just chaos. There is a sequence to the rolling. Alright, so what happens when I put a DC current through? So just a regular DC current. There's two things that happen. So I have, let's say if I have, so I put a DC current on, and let's call it negative 150 volts, just because I'd like to just keep it as being electrons, just for, you know, just to make the argument clearer. So the surface of all this wire is now covered in electrons. Denser at this end and weaker at this end. And each one of those electrons, let's just understand, is a polarizing filter. Alright, it polarizes in the sense that it creates a graviton, a magneton. If something goes through it, it turns it into one that it is doubly affected by. So it's 2x to electrons, and it's invisible to protons. So it's 0 to a proton. So a proton doesn't feel it at all, which means it's transparent to the field, and the electron is doubly influenced by the field produced when something goes through this electron. Okay, I mean, I used the word P there for polarization. I have to come up with another. I have to come up with some other P with a bottom to it. So when it goes through the filter, it is turned into, the gravity, the field, the generic field goes in through the electron, and it comes out the other side on all sides. All sides it's going in, all sides it's coming out, and it's coming out polarized. So I have to come up with some way to draw, maybe an arrow with a wider bottom or something. So I'll come up with symbols that'll make this more visual. But it goes in one thing, it comes out polarized, and in this case it comes out, in the electron's case, 2x sensitive to other electrons, so it's more likely to be absorbed by those electrons. Absorbed meaning the electron will suck it in, and that velocity of that graviton will now be part of the electron's movement. So the electron will move because it acquired that piece of field energy. And the inverse for the protons, which now won't feel anything coming from these electrons, these polarized electrons, and so the field from them will be invisible to the protons, and so that whatever pressure the protons have from behind them will now be stronger. So they'll have a tendency to want to be pulled. It's not really pulling. They'll tend to be pushed by the exterior. So anyway, so in this case, the positive is running through the center of the wires, and in a sense, the center of the coil. So if you could actually, do this, you would have both effects. You have essentially two fields are created. First, there's the field inside the conductor. The wires themselves will acquire this field, and then the interior will acquire exactly the opposite field, sympathetically. This is a better way to say that. Not the opposite field, the same field. Sorry. And you see, these are the little things you got to get. You got to get right. So you have too many electrons on the surface, and you have too few protons, and the field being created, the magnetic field. We really don't need that for now, so let's just deal with the current in the wire. So let me not worry about magnetic fields, that'll just confuse things. So anyway, so these are all surface, on the surface of all these wires are the negative. So they're all electrons on the surfaces. So you can sort of understand that if something's going through this conductor, if the field, so we talked about what's going to happen to the electron. So if it goes through the electron, it's going to come out this certain way. But you can sort of understand if all the protons are in the center and all the electrons are on the exterior, whatever goes in here is going to be electron polarized. It's not going to be polarized by the protons. It's only going to be polarized by electrons. So this entire field coming out of this coil is going to be all electron polarization. And it comes out straight, but I'm just using the progressiveness of the wire and the fact that the current's moving from this end to this end. This is the direction of the current, which tends to make you understand that if the polarizing filter is moving, then that gives it a little extra momentum in that direction. It gives the field movement in that direction. And so what's happening is exactly, you'll end up with the inverse circumstance. So here you start with 150 volts at this end, and now you're pushing in this wire, so the field comes in and it's going to push all the electrons, tend to push them in this direction. And so you're going to end up with 150 volts at this end, if these coils were equally run. Because you can sort of see that the high density, the strongest polarization is going to be here, the strongest effect. So you're going to have the most 2x polarization coming out of this end, and it'll get weaker, it goes over here. So it's weak at this end, and it's strong at this end. Those are bad, bad literacy. So it's strong at this end, this is the voltage end, and it's weak at this end. So the tendency is it's going to be pushing from strong to weak. And you're going to end up with exactly the opposite in this other coil, where you'll have the 150 volts at this end, you'll have most of the electrons at this end, and fewer electrons at this end. So this end will be your ground, you're close to a neutral, and this end is your plus 150 pressure electrons. So, I mean, plus is the wrong way to put it, because it's a plus of the electrons, which are the negative thing. See, that's what they got to fix that. It just makes this kind of retarded. All right, so that's the first thing that happens. So as soon as I put the current through, the first thing that happens is this voltage is established over here. But once it establishes the pressure, that's sort of it, right? It can't do anything else. The field just keeps pushing. It can only push 150 volts worth of pressure, so it can't go any higher. It's as high as the pressure will allow it to create. And so you're just stuck with a kind of a standing voltage that's sitting there. Now, theoretically, if you connected this conductor, the argument would be, well, why doesn't the voltage just go back to the beginning and then get pushed through this process again? Well, the problem with that is that when you are moving this current, this voltage actually disappears. So, I mean, that sounds not correct, but it's actually correct. Once this current starts moving, so once you initiate it, then you have the peak. It goes up, the current, and then it drops right off. I mean the voltage. And the only way you can really make it appear like there's a voltage in this wire is to essentially put something on the wire that prevents voltage from the current from moving. You have to kind of interrupt it. You have to put a coil with a little needle, in the stream to register the current moving, but there's really no voltage. So the problem is now is that this field is it just kind of de-energizes, because you don't have the same you're feeding pressure, but the pressure's automatically being relieved. So even though you keep pushing more pressure in, the pressure just drops because it can't maintain pressure. So the density of electrons diminishes, and the current moves. So you can move a lot of current. You can move a lot of electricity through the wire, but the amount of electrons on the surface diminishes because they keep getting relieved. They keep getting pulled into the ground. So they don't build up any pressure. You see what I said? They keep draining, I guess is the way to put this. As long as the conductor is conducting to the ground, it just drains these electrons, so they can't create the polarized filter. So the effect of their magnetism, their force effect, this polarizing effect shuts off. Just and you can sort of see that in the sense that they move less. They move slow. The electrons themselves are moving slow. So when they're moving slow, you could think logically they're not absorbing much and therefore they can't be creating much of a field, but they're also just not polarizing. So let's just keep with the polarizing word. So if they're not on the surface, and there's more protons now being able to balance, and so there's more protons, you know, it's more even, proton, electron, proton, electron. So now it's a more mixed field, and so that isn't conducive to creating any pressure, because it's, for every bit of pressure you're putting on an electron going one way, you're pulling it the opposite way the next time. So you're not being able to push any pressure into the other wire. So the whole thing just breaks down, because this voltage essentially drops to 0. Even though it technically has a voltage, but it only has a voltage you can, if you read it. There's no voltage unless you interfere with the function, and then you have a voltage in that tiny place where you blocked it, but you still don't have a voltage in the rest of the wire. You only have a voltage where you're creating a higher resistance and blocking the flow of the current. Yeah, that's the way to say it. Alright, so then what happens if you just cut it off? So you turn off the power supply, then the field drops. It's been able to maintain this pressure. Alright, now that's the part I'd have to, it's closing this circuit that kills this current. So if this current was open, if this circuit was closed, this would just end up, it goes up, and then it just, everything dies here too, because the voltage seeps out and there's no new voltage being created, because the voltage dropped in this wire. So you have your one peak and that's it. The tricky part is, like I said, when you get to the alternating current, then you have the rebound effect. And this would also, if you open this circuit, okay, then you could build up the 150 volts, turn this one off, and then close this circuit, and you could realize your little burst of 150 volts. Yeah, but that's pretty much it. Let's just go quickly to why alternating current works so well. But you can also do, so with DC current, all you can do is, so what you can do is you can, have this circuit closed, and you can just alternate the DC current, in the sense that you turn it on and off. But you're not going from positive to negative, you're just going positive, 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 positive. And you will be able to transfer voltage that way. It's technically alternating, but it's only alternating to the neutral, if you get what I mean. So it's going, so it just keeps doing the same thing as I described before. The voltage goes up as you initiate it, the pressure's high, and then as the pressure dissipates, yeah, how to put that? See, it takes time for it to get through the wire, so that's part of the problem, is it takes time for the electrons to move. So when you initiate the current, it doesn't move through the wire as fast as the pressure is building up. The pressure builds up quicker than the electrons can move through the wire, so that's why you end up with the polarized field at the beginning, and then it drops off. Yeah, that's probably the better way to say it. Alright, so then the alternating thing just ends up being the idea of that it's a more true magnet, and so the coil, is now going it's positive on the outside, and then it's negative on the outside, and then it's positive on the outside, then it's negative on the outside. And so by doing that, you're constantly changing the pressure, and so you're pushing the pressure both, you just keep going back and forth, and you get more of a sense of the true magnet, in the sense that this half goes positive on the outside, and then it goes negative on the inside, then it's negative, and then positive. So the two filters keep switching. Alright. Yeah, I don't want to beat this to death either. I still have to work on that, the fact that the voltage drop part is the part that's really important, and I have to get to, because that's what doesn't allow DC current to just keep pushing current. You would think that if the current's moving through this wire, you're still creating a magnetic field, and technically you are. I mean, you can create a magnetic field with a coil of wire, with a battery, a DC battery, and it'll maintain a magnetic field. But I have to, because that just doesn't, part of me saying, yeah, so if the field is still there, what's missing? I mean, why isn't it capable of still pushing? And the problem is because there's not adequate pressure. So even though it's still magnetized in the sense that there's still electrons on the surface and protons in the center, they're not nearly dense enough because of the voltage drop to produce enough of a field to induce current in another wire. Well, I'll work on that bit. But anyway, this basic design, I think, is just I want to get to the key to magnetism, the key to electricity is this idea of polarization, and the field is just the polarized gravity, the polarized quanta that are in the universe. They go through you, they come out, some tiny percentage of them comes out polarized based on the density of the filter. So again, at a high voltage, if I could, if I took this to 10,000 volts, it means the thickness of the electrons would be much thicker. It means they'd be polarizing more, and so they're creating a field denser in polarization, which means denser in its capacity to be absorbed by the electrons and to be ignored by the protons, depending on the polarization. Yeah, it's probably it. So anyway, so that part's solid. I just have to work some more on the field, the induction process needs work. So I'll work on it. Enough of that. So anyway, I think this is better than the other two videos anyway. Yeah. So wires are basically magnets. It's, a long wire is basically a magnetic. It's basically been converted into a magnet with poles. And it's a true dipole if you have a positive to a negative voltage. And it's a kind of hybrid monopole if it's to a ground. Yeah. So electricity can create poles that you can't create with magnetism. There's no such thing as a magnetic monopole, and there's certainly no hybrid. So in electricity you can have a monopole plus the idea of the hybrid of a pole to ground, just the south or just the north. Yeah. Okay. So till next time. In touch.